Hi everyone, I am Dr. Babaraj Bhaskar, Associate Professor in the Department of Chemistry at SRM Institute of Science and Technology, Katankulattu. In this lecture, I will be presenting an overview of corrosion types and their underlying electrochemical mechanism. This presentation will walk you through the types of corrosion and electrochemical mechanisms. Corrosion is the gradual degradation of metals through chemical or electrochemical reactions with their surrounding environment. Understanding its types and mechanisms is essential for engineering, infrastructure longevity, and material science. In essence, corrosion represents nature's tendency to restore refined metals to their lowest energy state through chemical or electrochemical reactions with the surrounding environment. Metals are gradually converted into more stable compounds, including oxides, hydroxides, and sulfides, leading to progressive material deterioration and loss of structural integrity. Rust is the most familiar phase of corrosion, tells the same story most plainly. Iron combines with water and oxygen to produce hydrated iron oxide, a brittle and flaky compound that continuously breaks away, exposing fresh uh, metal beneath and driving destruction deeper until nothing structurally sound remains. Exposed metals in open environment face relentless electrochemical assault from moisture, oxygen, and atmospheric pollutants, progressively dissolving the refined metal and leaving behind weakened and degraded material that can no longer serve its intended purpose. And when it comes to volcanic gases, rich in sulfur dioxide and hydrogen sulfide, have aggressively attacked the abandoned mining machinery, reacting with the metal surface to form sulfides and oxides that rapidly crumble the once functional structure beyond recovery. Interesting to note that India's vast coastal line, spanning over 7,500 kilometers, exposes metal to one of the most aggressively corrosive environment on Earth, where the combination of high humidity, salt-laden sea air, and elevated temperatures creates ideal conditions for rapid and severe electrochemical corrosion. Chloride ions from marine aerosols penetrate protective oxide layers on metal surfaces, disrupting passivation and triggering intense localized attacks such as pitting and crevice corrosion on steel structures, pipelines, ships, and coastal infrastructure. The warm tropical climate of India's coastal zones accelerate the rate of corrosion significantly. As higher temperature increases the kinetic energy of electrochemical reactions, causing metals to degrade far faster than in temperate environments. Industrial coastal cities such as Mumbai, Chennai, Vizag, and Kochi compound the problem further, where pollutants like sulfur dioxide and nitrogen oxides from industries combine with the marine moisture to form corrosive acids that intensify metal deterioration. The economic impact is enormous. Ports, naval vessels, offshore oil platforms, bridges, and reinforced concrete structures along India's coastal zone suffer billions of rupees in corrosion related damage annually, making coastal corrosion management a critical priority for the nation's infrastructure and industrial structure. In fact, India loses approximately US dollar 100 billion to corrosion annually. This is the report released by Jindal Stainless Steel during International Summit on Corrosion Technology and Management. Most metals, except noble metals such as gold, platinum, etc., exist in nature in combined forms as their oxides, carbonates, hydroxides, uh, sulfides, chlorides, and silicates, and are artificially reduced to their pure metallic state during the extraction, uh, placing them in a thermodynamically excited higher energy condition. This elevated energy state creates a natural and spontaneous tendency for metals to revert back to their original combined forms, and driving the corrosion process the moment metals are exposed to environmental agents such as moisture, gases, or liquid. Corrosion is therefore not merely a chemical nuisance but a fundamental thermodynamic inevitability. The metal's relentless drive to return from its unstable refined state to the lower energy stable compounds from which it was originally derived. In other words, very corrosion story begins at the surface, the point where metal meets its environment, whether through direct chemical reaction or electrochemical attack involving electron transfer. The metal begins to deteriorate from the outside in. Simply put, corrosion is any unwanted process, destruction, or deterioration of a solid metal starting at its surface through chemical or electrochemical interaction with the surrounding environment and resulting in a measurable loss of material and performance. When iron is exposed to atmospheric condition, it undergoes oxidation in the presence of moisture and oxygen, resulting in the formation of a reddish, flaky layer of hydrated iron oxide, commonly known as rust, that progressively weakens the metal by compromising its structural integrity. Similarly, copper exposed to moist air containing carbon dioxide develops a distinctive green patina on its surface formed by the deposition of basic copper carbonate plus copper hydroxide, which, unlike rust, acts as a partially protective layer retarding further corrosion beneath. Now let's talk about the types of corrosion. This PPT explains the types of corrosion and divides them into two major categories. One is dry or chemical corrosion, and the another one is the wet or electrochemical corrosion. Dry or chemical corrosion happens due to direct chemical action of the environment or atmospheric gases like oxygen, hydrogen sulfide, sulfur dioxide, or by anhydrous inorganic liquids acting on metal surfaces. Its main types are oxidation corrosion and then corrosion by other gases and liquid metal corrosion. Wet or electrochemical corrosion occurs when a conducting liquid touches a metal or when two dissimilar metals or alloys are immersed partly or fully in a solution. In short, the chart shows that corrosion can happen either by direct chemical reaction in dry condition or by electrochemical action in the presence of a conducting liquid. Let's discuss the dry or chemical oxidation corrosion. This type of corrosion occurs through direct reaction of oxygen with metals, typically in the absence of moisture, and its severity is strongly governed by temperature. When it comes to ordinary temperature, most metals are only mildly affected. When it comes to low temperature, highly reactive metals such as alkali metals like lithium, sodium, potassium, rubidium, etc., and alkaline earth metals, beryllium, calcium, strontium, etc., are even rapidly getting oxidized, even when the temperature is very low. When it comes to high temperature, nearly all metals oxidize readily The notable exceptions being the noble metals, silver, gold, platinum, which resist oxidation even at elevated temperatures. Reactions in oxidation corrosion, where oxidation takes place at the surface of the metal forming metal ions, where metal loses electron, therefore metal becomes metal ion. In turn, oxygen accepts the electron released by the metal and it becomes oxide. So, overall reaction is of oxide ion reacts with the metal ions to form the corresponding metal oxide film. As you can see here, the reaction is clearly depicts the metal oxide formation. Having discussed the first type, oxidation corrosion, the next one is the corrosion by other gases. When it comes to gases such as sulfur dioxide, carbon dioxide, chlorine, hydrogen sulfide, fluorine, etc., the severity of gas corrosion depends primarily on the chemical affinity between the metal and the attacking gas, and critically on the nature of the film formed on the metal surface. It could be two types. One is protective or non-protective porous films. So when it comes to protective or non-porous films, acts as a barrier, shielding the underlying metal from further attack. So corrosion slows down or stops over time. So good example is chlorine attacking silver, which forms a dense silver chloride film, right? Silver chloride film that halts further corrosion. Therefore, it becomes protective or non-porous corrosion. And whereas another example for non-protective or porous corrosion, uh, they fail to shield the metal, leaving it continuously exposed. Corrosion progresses until the metal is fully destroyed. Example is the dry chlorine on tin, SN, forms volatile tin tetrachloride, which immediately evaporates, constantly exposing the fresh metal surface for further attack. Therefore, the entire metal would get destroyed. This is called uh, porous or non-protective corrosion. And another example for this, hydrogen sulfide on steel. In petroleum industry, at a high temperature, forms a porous iron sulfide scale that not only fails to protect but also interferes with the normal industrial operations. Now we can see how we can measure whether the particular corrosion is protective or non-protective, or porous or non-porous corrosion using the pilling bedworth ratio. When it comes to pilling bedworth ratio, explains nature of oxide fill, that's a porous or non-porous. The volume of oxide divided by volume of metal consumed. If volume of oxide is less than volume of metal consumed, then the oxide layer is porous and it could be non-protective. While if volume of oxide formed is greater than the volume of metal consumed, then the oxide layer is non-porous, then it becomes protective. So conclusion, the filling bedworth ratio predicts corrosion resistance of metal. This is very important one to calculate the whether to understand the corrosion, whether it's porous or non-porous. Having discussed the first two types from the oxidation or dry corrosion, that's oxidation corrosion or corrosion by other gases, the third one is the liquid metal corrosion. When it comes to liquid metal corrosion, this type of corrosion occurs when a flowing liquid metal at high temperature chemically attacks a solid metal or alloy. It is particularly relevant in nuclear power devices where liquid metals are used as coolants. The attack occurs through two mechanisms. One is dissolution. The solid metal is directly dissolved into the flowing liquid metal. The other one is internal penetration. The liquid metal seeps into the solid metal's internal structure. Both modes ultimately weaken the structural integrity of the solid metal, making liquid metal corrosion a critical concern in high temperature nuclear application. The next type would be the wet or electrochemical corrosion and its mechanism. That would be discussed in the separate section in the next video. Thank you.